Hello. Today I want to talk with you a little bit about assigning oxidation numbers or states, as our book commonly refers to them, and how that relates to redox reactions. Many of us at home have a checkbook. One of the things about a checkbook is you have to keep it balanced. So we use a check register to record the debits or deductions from our account and deposits or additions to our account. Oxidation numbers or states help us to keep track of the movement of electrons throughout a chemical reaction. Any type of chemical reaction that is not a precipitation reaction in some way or another involves the movement of electrons. This is why keeping track of oxidation numbers and keeping track of electrons is so very important. Today, I'm going to spend a few minutes going over the rules for assigning an oxidation number or state to any element within a compound. And then we'll look at an example. Finally, we'll look at how we can apply what we learned to a chemical equation like you see on the right side of your screen to assign oxidation numbers to every element in that equation and decide what substance is oxidized and what substance is reduced. Let's begin with the rules for assigning oxidation numbers or states. I wish I could tell you there was a shortcut to remembering these rules, but there isn't. Unfortunately, this is a straight-up memorization task and something you must become very familiar with prior to your next exam. The first rule for assigning oxidation numbers and states is that elements in their elemental form have an oxidation state or oxidation number of 0. The oxidation number of a monoatomic ion is the same as its charge. So a sodium ion in sodium chloride has a 1+ charge, and it has a +1 oxidation number. Notice that in the oxidation number, I list the charge first, then the number. And in a charge, I list the number first and then the sign. Rule number 3 says that nonmetals tend to have negative oxidation numbers, although some are positive in certain compounds or ions. This rule is very general. Let's look at the specifics. The first thing you need to know about nonmetal oxidation numbers is that the oxidation number of oxygen is almost always -2. The lone exception is when it appears in peroxides like hydrogen peroxide, H2O2, and in those cases it is -1. We won't be working much with peroxides in this course, however you may see them in the future. Second thing you need to know about nonmetals. Hydrogen is generally -1 when bonded to a metal and +1 when bonded to a nonmetal. This always holds true. The third thing you need to know about nonmetals are picky in case you haven't figured that out yet, is that fluorine always has an oxidation number of -1. The final thing you need to know about nonmetals is that halogens, chlorine, bromine, iodine, tend to have an oxidation number of -1 when they are negative ions. However, if they are part of a polyatomic or oxyanion like chlorate, then they can have a positive oxidation state. In other words, what I'm telling you here is that oxygen takes precedence in terms of nonmetals. Oxygen is always -2, fluorine is always -1, and they sort of bully the other nonmetals into being whatever they have to be. If oxygen or fluorine are present, take care of them first, then deal with the rest of the nonmetals. Rule 4 says that the sum of the oxidation numbers or states in a neutral compound has to add up to 0. And Rule 5 says the sum of the oxidation numbers in a polyatomic ion is equal to the charge on that ion. Let's look at an example to illustrate these rules. This example will not hit every rule. You will see many more examples in class, in your textbook, homework, quizzes, etc. Work as many of these example problems as you can because there are many, many different combinations. In our example, we're going to ask, what is the oxidation number of each element in magnesium nitrate? Magnesium nitrate is made up of three ions. One of those ions is Mg2+, the other two are NO3 1- or nitrate ions. Mg2+ is a monoatomic ion. Recall from our rules that monoatomic ions have oxidation numbers equal to their charge. Therefore, Mg2+ has an oxidation number of +2. In terms of nitrate, NO3 1-, the sum of the oxidation numbers of N and O, according to the rules, must add up to -1. Oxygen gets precedence and preference here, which means oxygen's oxidation number is -2. 3 times -2 is -6. This means in order for the oxidation numbers to add up to -1, nitrogen must be +5. +5 plus 3 times -2 gives us -1. Again, work as many of these examples as you can to understand how to properly assign oxidation states or numbers to all elements in a compound. Let's switch gears a bit and look at how we can apply these ideas to a chemical reaction. Chemical reactions that involve the transfer of electrons are affectionately referred to as oxidation reduction reactions, or for short, redox reactions. In redox reactions, one substance is oxidized, one substance is reduced. Those processes always happen in pairs. If you look at the reaction and assign oxidation numbers to every element in the reaction, it is very easy to identify what is oxidized and what is reduced. On the screen in front of you, you see the reaction of solid zinc plus 2 H+ ions, 2 hydrogen ions, reacting to form aqueous zinc 2+ ions and hydrogen gas. You'll note that we have assigned an oxidation number to each element. The zinc solid has an oxidation number of 0 because it's an element in its elemental standard state of a solid. H+ is a monoatomic ion, so its oxidation number is +1. Zn2+ is a monoatomic ion, so its oxidation number equals its charge, charge of 2+, oxidation number +2. H2 is hydrogen gas. That is the elemental form of hydrogen, and therefore it has an oxidation number of 0. A species is oxidized when it loses electrons. Here, zinc loses 2 electrons to go from neutral zinc, metal, to the zinc 2+ ion. Note that the oxidation number of zinc becomes more positive as you move from reactants to products. This is the indication that zinc is oxidized. In a similar vein, a species that is reduced gains electrons. Here, each of the H plus gains an electron and they combine to form H2. Notice as you go from H plus on the reactant side to H2 on the product side, the oxidation numbers go from +1 to 0. The oxidation number got more negative as you move from reactants to products. This is a sign that hydrogen is reduced. The substance that is reduced is also referred to as the oxidizing agent. The substance that is oxidized is referred to as the reducing agent. In other words, if you can figure out what is oxidized and what is reduced, you can figure out the oxidizing agent and the reducing agent. The species is always the opposite type of agent. If it is reduced, it is the oxidizing agent. If it is oxidized, it is the reducing agent. In the reaction shown on the screen, H plus is reduced. It picks up an additional electron, causing zinc to be oxidized because zinc gives up its electron to H plus, and therefore H plus, which is reduced, is the oxidizing agent. In contrast, zinc reduces H plus. Zinc gives up an electron. H plus picks it up. Since H plus gained an electron, it is reduced. Zinc is oxidized, and it is the reducing agent. The arguments for what makes something an oxidizing and reducing agent get confusing quickly. It is much easier to realize that if a substance is reduced, it is the oxidizing agent, and if it is oxidized, it is the reducing agent. Much like assigning oxidation numbers and states to every element in a chemical compound, it is vital that you practice identifying what is oxidized and what is reduced in a chemical reaction, and in order to do that, you must assign oxidation numbers to each element in the reactants and the products.